Lighthouse Scientific Education presents a lecture in the electrochemistry series. The topic, redox, oxidation numbers, and half reactions. Material in this lecture relies on an understanding of the previous lectures, types of chemical reactions, and balancing chemical equations. Using what was covered in the chemical reactions lecture, a review and expansion on what is meant by redox reaction is given. That leads to an introduction of oxidizing and reducing agents. Then it is on to a deeper discussion of redox reactions, including oxidation numbers and half reactions. The next lecture in this series combines these two last topics and develops a process for solving full redox reactions. Not all students will need that level of understanding, so be aware of what is expected of you. What does the term redox actually mean? Redox is short for reduction and oxidation. As we saw in the chemical reaction lecture, the oxidation-reduction reaction, or reduction-oxidation reaction, is listed as a type 5 reaction. Some redox reactions also fall under the synthesis or single displacement reaction category. The term oxidation was originally used to describe the reaction of an element, usually a metal, with oxygen. That is where the OX comes from. Examples of such reactions are the rusting of iron and the burning in combustion. The thing to remember about oxidation and reduction is that they belong to the same reaction. There is no oxidation without reduction, and there is no reduction without oxidation. So the overall reaction can be viewed as having two parts. Reduction refers to the gain of an electron or electrons. Silver ion can gain 2 electrons and become the element silver. The electrons are explicitly written in this form of a balanced equation. Oxidation refers to the loss of an electron or electrons. The element copper can lose 2 electrons and become the copper ion. Gaining electrons has electrons as reactant. Losing electrons has electrons as a product. The direction of the flow of electrons can be confusing, but there's some helpful acronyms for keeping the connection between oxidation reduction and loss gain straight. There is oil rig. It is the first letter of each word in oxidation is lose and reduction is gain. The other common acronym is Leo-Ger. That is, Leo the lion roars a ger. It stands for lose electron, oxidation, gain electron, reduction. Either way will work, but do have a way to keep the direction of electron flow straight. Since oxidation and reduction are two parts of the same reaction, certain compounds in the reaction can be assigned and named as either causing production or consumption of electrons. An oxidizing agent is a chemical that causes oxidation in another substance. Oxidation is lose. Oxidizing agents cause loss by being reduced in the reaction. Reduction is gained. Loss and gain are tied together. In the reaction above, the silver ion and the copper ion are oxidizing agents. They are both reduced. It is not as simple as selecting the reactant or the product. It is whether electrons are gained or lost. The other side of the coin is the reducing agent. It is the chemical that causes reduction in another substance. Rig, reduction is gain. Reducing agents cause gain by being oxidized in the reaction. Oxidized is loss. The elemental forms of the metals of silver and copper are reducing agents. So, a redox reaction will have a compound that gains an electron and one that loses an electron. The terms oxidation and reduction refer to what is happening to that specific compound in the reaction. and the term agent is assigned to what a compound does to another compound in the reaction. Yet another layer of possible confusing terminology. At some point, the student has to sit down and get the direction of gain and loss straight, and the sooner the better. An important question here is to ask, how do we know which compound is an oxidizing or reducing agent? Well, the short answer is to consult a table. The transfer of electrons is not something a student can generally predict. Most textbooks will have a list of reactions that show the reduction of elements and compounds. As reduction, they are all written with the electron or electrons as reactants. Therefore, the compound in the reactant is the oxidizing agent. It gets reduced. And the compound in the product is the reducing agent. It gets oxidized. Since not all oxidizing agents are created equal, the table generally lists them in order of strength. The weakest or poorest oxidizing agents are at the top, and the strongest are at the bottom. Can a reaction have both a weak oxidizing agent and a weak reducing agent? No, it cannot. If the oxidizing agent is weak, then the reducing agent is strong. If the oxidizing agent is strong, the reducing agent is weak. Expanding on this, take the first reaction. It has lithium ion gaining an electron and forming the metal lithium. Consulting the periodic table, we see that lithium is a column 1 alkali metal. These metals readily lose an electron and form +1 ions. That makes lithium metal a strong reducing agent. This reaction is stronger in moving from product to reactant. Lithium ion does not readily pick up an electron and reform the elemental form. That makes it a weak oxidizing agent. At this level of chemistry, lithium ion is generally not shown to pick up an electron and reform the element. That makes it a weak oxidizing agent. One way is strong, and the other weak. On the other end of the scale is the reaction with fluorine. Fluorine is in the column of halogens, which are next to the noble gases. Halogens readily accept an electron and form -1 ions. As such, the elemental fluorine, F2, makes a strong oxidizing agent. It readily accepts electrons and becomes reduced. The ion form, however, does not readily give up its gained electron, so it is a poor reducing agent. If one form of agent is strong, then the other form is weak. Nothing is good at both accepting and donating an electron. It's one or the other. We can use what we know about ion formation to give us a sense of strong and weak oxidizing and reducing agents. But it requires a comfortable understanding of the terms. An oxidizing agent is itself reduced. That means it gains electrons. It has to get those electrons from some other compound. Therefore, it causes oxidation in the other compound. On the other hand, a reducing agent is itself oxidized. It loses electrons. Those electrons have to go somewhere. They end up being taken in by another compound. Reducing agents cause reduction to that other compound. Spend some time with this table until you have a decent grasp of the terminology. There's no subject in an introductory chemistry course that so easily becomes tangled up in direction. Now, to handling redox equations. And the degree that a student needs to be able to do this is dependent on their particular course. This lecture will aim at components needed to solve a redox reaction. The next lecture pulls the pieces together and uses an organized procedure that can actually balance a full redox reaction. Not all students will need to go that far in their study. As always, be aware of what is expected of you in your course. All right, a couple points to give us additional perspective on the subject. We begin by restating that if there is oxidation, then there is reduction, and vice versa. Reactions with elements are always redox reactions. If an element reacts, it will either gain or lose an electron. Nonmetal elements tend to gain electrons. They often form anions. Consulting the periodic table has nonmetals in this region and includes the strong oxidizing agent fluorine, as we saw earlier. Fluorine tends to gain an electron and become reduced. Metal elements tend to lose electrons. They often form cations. That is the case with the first two columns of the table, including the strong reducing agent, lithium. That takes care of elements. What about compounds and polyatomic ions? Those tend to be more difficult to identify. Determining oxidation or reduction agent will employ a process that we have not come across before. It is centered on the oxidation number of the atoms in the compound, and it is a topic that we will need to discuss further. First of all, the oxidation number is a construct. It's not a real thing. It is a tool to help us follow where the electrons are going in a reaction. The oxidation number, abbreviated OX, number sign, or pound, or hashtag, can more or less be defined as the number of electrons that an atom either gains or loses when it forms a chemical bond with another atom. It is also defined as the charge an atom would have if electrons in its bonds belong completely to the more electronegative atom. Of course, that doesn't really happen. Neither of these definitions are particularly satisfying, but we are more interested in its application than its origin. As an application, it is very useful. The oxidation number is called the oxidation state of that atom, and every atom in a compound will have an oxidation number or oxidation state. That is where we need to go. In a redox reaction, in going from reactant to product, if the oxidation number of an atom or ion goes up, the atom or ion is oxidized. That is, it will have lost an electron or electrons in the reaction. Oxidation is lost. If, however, the oxidation number in going from reactant to product goes down, then the atom or ion is reduced. There will be gaining of electron or electrons in the reaction. Reduction is gain. With this in mind, we can ask the first important question. How do we get the oxidation number for the atoms in a reaction? Fortunately, there are some good rules of thumb to make the process much easier than it may first seem. Beginning with the rule of thumb that an atom in its elemental form will always have an oxidation number of 0. 0 for iron metal, 0 for each hydrogen in H2. This makes sense by the definition of the oxidation number a charge on an atom would have if the electrons in its bond belong completely to the more electronegative atom. For elemental iron, it makes no bonds, so it keeps all of its electrons, and its oxidation number is the charge on the atom, 0. The oxidation number of a monatomic ion, an ion with only one type of element, always equals the charge on the ion. Same argument can be made that these ions are not making bonds, so they get an oxidation number equal to their charge. Calcium has an oxidation number of +2, just like its charge. The sulfide ion has an oxidation number of -2, just like its charge. As for atoms in a compound, the process becomes a little more complicated. There are some common occurrences that help reduce the complexity. The oxidation number of fluorine is always -1. With oxygen, the oxidation number is usually -2. This is one to remember. In a compound, the hydrogen atom usually has an oxidation number of +1. There are instances where hydrogen forms a metal hydride like calcium hydride, CaH2, where the oxidation number of hydrogen is M-1. That doesn't come up very often, so stick with the +1. The other important thing to keep in mind when determining oxidation numbers is that the sum of the oxidation numbers of atoms in a neutral compound is 0. A neutral compound has a charge of 0, and the oxidation numbers have to reflect the distribution of those electrons. For example, H2O is a neutral compound. Assigning its 3 atoms oxidation numbers as suggested, the hydrogen is a +1, the oxygen is a -2, has the math 1 + 1 - 2 = 0, neutral. Contrast that with the sum of the oxidation numbers of atoms in a polyatomic ion being equal to the charge. For the polyatomic anion hydroxyl, the sum of the oxidation numbers is the -2 of oxygen plus the +1 of hydrogen for a value of -1, just like the charge. Keeping these two panels of parameters as reference panels, we will set about finding the oxidation number for atoms not specifically identified on this list. What is the oxidation number of the nitrogen in NF3? A systematic approach should clarify the process of getting the oxidation number of one atom in a compound, and it begins by writing out the compound as individual atoms. NF3 has 1 nitrogen and 3 fluorines. Next, we ask ourselves if we know the oxidation numbers for any of these atoms. Turns out that we do. Fluorine is said to always be -1. Put a -1 value below each of the fluorines. Is there any advice on the nitrogen? No, there is not. Put a question mark or variable to hold that unknown value. The other piece of relevant information to be gathered from the reference panels is that the sum of the oxidation numbers in the compound is 0. That should be added to the summation of the oxidation numbers of the atoms in the compound. What is left is arithmetic. Combine the 3 - 1 values together for a -3 and ask, what value -3 is equal to 0? The equation, of course, solves to +3. The oxidation number of nitrogen in NF3 is +3. Does nitrogen always have a +3 oxidation number? No, it doesn't. Nitrogen's oxidation number is dependent on the atoms it is bound to. That is true for almost all atoms, and is why this type of procedure is needed to determine oxidation numbers. Another example asks us to find the oxidation number of manganese in permanganate ion, MnO4 - 1. A good place to start is with all the atoms in the ion listed out as individual atoms, 1 magnesium and 4 oxygens. Next, we check the reference panels to see if there's not some suggested value for any of the atoms in the ion. The list tells us that oxygen is usually a -2. And while we have that highlighted, we might as well cover an example where oxygen does not have a -2 oxidation number. Try the oxygen atoms in O2. If each oxygen atom had an oxidation number of -2, then O2 would have a sum value of oxidation numbers of -4. As we saw earlier, O2 is the elemental form of oxygen and therefore has an oxidation number of 0. So, there are cases where this rule of thumb does not hold. Returning to permanganate, add a -2 for each oxygen. Is there a suggestion for the manganese? No, there's not. Manganese is the unknown. Do we know what the oxidation numbers in this ion should sum up to? According to the reference panel, in a polyatomic ion like permanganate, the oxidation numbers should sum to the charge on the ion. That's a -1. With the numbers in place, we have an equation with a single unknown which can be solved for. The 4 minus 2 values combine to a -8. What value, when combined with a -8, yields a -1? That is +7. The oxidation number of manganese in permanganate is +7. That's much larger in magnitude than the 1s, 2s, and 3s we've been dealing with so far. And it goes to show that oxidation numbers are not so much a real value, but rather a tool for determining the flow of electrons. That point is made in greater detail in the next lecture. We still have one more example of getting oxidation numbers to cover, and this one wants to know the oxidation number for carbon in carbonic acid. This example has 3 kinds of atoms: 2 hydrogens, 1 carbon, and 3 oxygens. As with the previous example, the oxygens will be assigned an oxidation number of -2. They are not, however, the only atom type to be mentioned in the reference panel. Both hydrogens should be assigned a +1 value. And the carbon? That's the unknown. Half of the summation equation is complete. What should these values sum up to be? Carbonic acid is a neutral compound, and the summation of oxidation numbers has to be 0. Almost there. The 2 hydrogens sum to a +2, and the 3 oxygens sum to a -6. +2 minus 6 is -4. This expression simplifies to the oxidation number of carbon -4 equals 0. What value -4 is equal to 0? A +4. As long as the oxidation number of only one atom type in a compound or ion is not known, it can generally be solved for. There are additional examples of getting oxidation numbers in compounds and ions in the half reaction part of this lecture, and in the balancing of equations in the next lecture, specifically in problems 3 and 4. Prior to taking on full redox reactions is developing an understanding of balancing half reactions. That is because some reactions that balance by atom do not balance by charge. For example, the net ionic equation of aluminum metal plus silver ion forming aluminum ion and silver metal. The atoms are balanced, but there's a +1 charge on the reactant side and a +3 charge on the product side. The charges can be balanced by adjusting the coefficients in front of silver ion and silver metal to 3. Now the atoms and the charges are balanced. Up till now, the first equation would have been a satisfactory balancing. Understanding that this is a reaction that transfers electrons tells us that we need to take a deeper look at balancing. The deeper look begins with the half reaction. It is a mechanism to look at the reaction in parts. The half reaction is not a real reaction. It is only a way to keep track of the movement of electrons. It is a bookkeeping trick. Each redox reaction can be broken down into 2 half reactions. Still, there is only one real reaction. One half reaction looks at just the reduction part of the reaction. The silver ion is an example of just the reduction part of a reaction. Another half reaction looks at just the oxidation part of the reaction. The copper metal is an example of just the oxidation part of the reaction. These half reactions do not occur on their own. As will be shown in detail in the next lecture, the 2 are recombined to give the correct balanced redox reaction equation. Balanced here means balanced atoms and balanced charge. A preliminary example of the process is given here with the two half reactions listed above, recombining into a single redox reaction. Reactants of the half reaction are added together, and the products of the half reactions are added together. Both sides of the redox reaction have the same number of electrons. Since the number of electrons are equal on the two sides, they can be removed. At some point in balancing a redox reaction, the electrons will have to cancel out, because the number of electrons lost in oxidation is equal to the number of electrons gained in reduction. There are no spare electrons. The simplified equation looks more like the type of equation we are used to seeing with atoms being balanced. Note that both sides of the reaction have a net charge of +2. Charge is also balanced. Atoms, electrons, and charge are all balanced. A final point. It is common for a balanced redox reaction to be written as a net ionic equation. Spectator ions are generally removed. Ultimately, the goal of balancing a redox reaction is combining half reactions such that electrons cancel out. To get there, we need to back up and develop an understanding of how to take a full reaction and establish half reactions, and then to be able to balance those half reactions. First is separating out the half reactions from the full redox reaction. A redox reaction will involve a change in the oxidation number for two or more elements in going from reactants to products. So, an oxidation number has to be determined for each element, and that includes the element on both sides of the equation. To make matters less cluttered, unless there's an O2, an H2, or a metal hydride, like calcium hydride, the oxidation number of oxygen and hydrogen does not change, and for the most part, we can ignore them in getting half reactions. In a redox reaction, if the oxidation number of an atom or ion goes up, the atom or ion is oxidized. Oxidation is loss. If the oxidation number of an atom or ion goes down, then the atom or ion is reduced. Reduction is gain. For example, let's bring back the silver-copper equation and roll out the oxidation numbers for each species in the reaction. In covering the establishing of half reactions, the oxidation numbers will be treated as if they have already been determined. Looking at the oxidation numbers for just silver and going from reactant to product, the oxidation number decreases from a +2 to 0. If the oxidation number goes down, the atom or ion is reduced. This is the reduction part of the equation. Take out just these species and establish a half reaction. Now, looking at the copper, in going from reactant to product, the oxidation number increases from 0 to +2. If the oxidation number goes up, the atom or ion is oxidized. This is the oxidation part of the equation. Pull the copper out and establish a half reaction. A redox reaction broken down into half reactions. One more, and it uses an equation that will come up again in the next lecture. The oxidation number for the elements in their elemental form is 0, and monatomic ions take on their charge. Looking at just the oxidation numbers for the bromine, in going from reactant to product, the oxidation number increases from a -1 to 0. If the oxidation numbers go up, the atom or ion is oxidized. This is the oxidation part of the equation. Pull the bromide and bromine out and establish a half reaction. Now looking at the chlorine. in going from reactant to product. The oxidation number decreases from a 0 to -1. If the oxidation number goes down, the atom or ion is reduced. This is the reduction part of the reaction. Taking out just the chlorine and chloride establishes the other half reaction. Now that we have a means of getting a half reaction, how do we balance them? The process is the same for reduction or oxidation half reactions, and we will focus on balancing under acidic conditions. Later, there'll be a small modification for handling basic conditions. Begin by balancing the atoms in the half reaction. This is not always as straightforward as it is in a full reaction equation, because sometimes there are atoms that are not on both sides of the half reaction. Usually these atoms are hydrogen or oxygen, because the reaction takes place in an aqueous solution, and a water molecule is providing those atoms. To handle this, it is okay to add H2O, an aqueous hydrogen ion, to balance the oxygens and hydrogens in the half reaction. Again, this is a process for acidic conditions. Next, balance the charge in the half reaction. There should be an ion somewhere in the equation, and that will make the two sides of the equation have different charges. Balance the charges by adding a -1 charged electron or electrons to one side of the equation. Sometimes that is adding the negative charge to one side, and sometimes that is reducing a positive charge on another side. The last point is one many students will not be asked to do. It is balancing the half reactions in a basic solution. This is done after steps A and B. For each hydrogen ion in the equation, add a hydroxyl ion to both sides. Essentially, this exchange is basic for acidic. Since after this addition, there will be both hydrogen ion and hydroxide ion on the same side of the equation, combine hydroxide and hydrogen ion into H2O. When this is done, there will no longer be hydrogen ion in the equation. If this combination causes water to be found on both sides of the equation, cancel out excess waters. If your instructor does not expect balancing in basic solutions, then skip past those parts of the lecture. To develop a better understanding of balancing half reactions, 3 examples are given. Example 1. What is the balanced half reaction of chlorine going to chloride ion? Familiar to us is the balancing of atoms. This is done easy enough by adding a coefficient of 2 in front of the ion chloride. What about charge? Is the charge the same on both sides? It is not. On the reactant side, the net charge is 0. Chlorine is a neutral molecule. On the product side, it is 2 times -1, for a net charge of -2. How do we get both sides of the equation to have an equal charge? The only way is to add one or more negatively charged electrons. Should we add them to the reactant or product side? Which side needs more negative charge to balance the charges? Yes, the reactant side. It needs a net charge of -2. How many electrons does it take to get a -2 charge? It takes 2 electrons. This is a balanced half reaction. Atoms are balanced, charge is balanced. How about balancing the Fe2 to Fe3 equation? This one starts out easy enough because the atoms are already balanced. Charge, however, is not balanced. The reactant side has a +2 charge, while the product side has a +3 charge. It would be nice to be able to add an additional positive charge to the reactant side, but that is not an option. Only negatively charged electrons can be added. From a mathematical perspective, the only way to change the charge is to add a negative charge to one of the sides. But to which side and how much negative charge? Add a -1 to the product side, giving both sides of the equation a net charge of +2. +3 minus 1 is +2. From a chemical equation perspective, balancing charge is adding a single electron to the product side. So far, so good. Let's step it up a bit and balance the more complicated reaction involving chromium-3 and chromate. Begin by balancing the atoms, and a survey of the equation shows that chromium is balanced, but oxygen cannot be balanced since oxygen is not currently found on both sides of the reaction. The second part of the first step is needed here. The equation will need to be expanded to account for the 4 oxygens on the product side. According to the rule, oxygen is balanced by adding water to the opposite side of the reaction. 4 oxygens are balanced by the addition of 4 waters. 4 waters have 4 oxygens. That takes care of the oxygen, but it introduces a new element in the process. The reactant side now has hydrogens. The product side will need to acquire some hydrogens. According to the rule, hydrogen is balanced by adding hydrogen ion to the opposite side of the reaction. 4 waters introduce 8 hydrogens to the reactant side. 8 hydrogen ions are therefore introduced to the product side. With that, each side has 8 hydrogens, 4 oxygens, and 1 chromium. The atoms are balanced. This type of balancing is a process. Know the steps and follow them. Now, to charge. Do the reactants have the same net charge as the products? On the reactant side, only the chromium-3 has a charge. The charge on the reactant side is +3. On the chromate side, both the chromate and the hydrogen ions bring charge. Chromate is a -2, and 8 singly charged hydrogens bring a +8 charge. That can be simplified. -2 plus 8 is +6. The two sides are not balanced by charge. The only way to balance them is to add negatively charged electrons to one side. To what side and how many negative charges need to be added? Well, adding a negative value to +3 will only make it smaller. So we will not be adding electrons to the reactants. Adding negative charge to a +6 will make it smaller. Specifically, adding -3 charge to +6 will make the net charge on the product side equal to the charge on the reactant side. To add a -3 is to add 3 electrons. This is a balanced half reaction, and it's almost as difficult as these half reactions get. Almost. For demonstration purposes, we will look at what it takes to modify the half reaction for basic conditions. In a basic solution, there are few hydrogen ions, and they are quickly picked up by some of the many hydroxide ions to reform water. As such, the half reaction is better served balancing the excess hydrogen with the hydroxide ion rather than the hydrogen ion. Since this balancing thing is just a process, an additional few steps can clear the hydrogen ion out and replace it with hydroxide. The first step is that for each hydrogen ion, add a hydroxyl anion to both sides of the reaction. Let's give ourselves some room here. There are 8 hydrogen ions on the product side. We need to add 8 hydroxyl ions to the product side and the reactant side. If we add the same amount of hydroxyl ion to both sides of the reaction, the atom and charge aspect of the equation stays balanced. We do not want to have to rebalance the equation. The second part is to combine hydroxyls and hydrogen ions into water. This is the same reaction covered in the acid-base series of lectures. On the product side, there are 8 hydrogen ions that can combine with 8 hydroxyl ions to form 8 water molecules. Nothing has really changed. The atoms and charges that were 8 hydrogen ions and 8 hydroxide ions are now in the 8 water molecules. All that has really occurred is that the hydrogen balancing, originally done by 8 hydrogen ions, is now done by 8 hydroxide ions. That this reaction is still balanced may or may not be readily apparent, so a double check is in order. On the reactant side, there are 16 hydrogens, 12 oxygens, and 1 chromium. That's the same tally as on the product side. Atoms are balanced. A look at charge has a net charge of -5 on the reactant side and a -5 on the product side. There's still one more step. Adding hydroxide ion has created some water. The final step is to clean up the excess waters. There are waters on both sides of the reaction. All 4 of the waters on the reactant side will cancel out with 4 of the 8 waters on the product side, leaving just 4 waters. This half reaction can be balanced under acidic or basic conditions. A thing to note is that the hydrogen ion under acidic conditions is on the opposite side of the equation from the hydroxide ion under basic conditions. There will also be a change in the number of waters in this process. And that completes the material of this first lecture concerning redox chemistry. As a recap, redox is short for reduction and oxidation. Reduction refers to the gain of an electron or electrons. Oxidation refers to the loss of an electron or electrons. An oxidizing agent is a chemical that causes oxidation in another substance. A reducing agent is a chemical that causes reduction in another substance. If there is oxidation, then there is reduction, and vice versa. They come in a pair. An oxidation number can be described as the number of electrons that an atom gains or loses when it forms a chemical bond. It is not a real thing, but a way to monitor the flow of electrons in a reaction. It is also called the oxidation state of that atom. There are some rules and common occurrences with oxidation numbers. The elemental form of an atom always has an oxidation number of 0. Monatomic ions have an oxidation number equal to their charge. Fluorine is a -1, and oxygen is usually a -2, and hydrogen is usually a +1. The sum of oxidation numbers of the atoms in a neutral compound is 0. The sum of oxidation numbers of the atoms in a polyatomic ion is the charge on the ion. A half reaction is either just the reduction or just the oxidation part of a reaction, not both. Solving redox reactions involve balancing half reactions. The atoms are balanced in the half reaction. Water and hydrogen ion can be added freely to balance oxygen and hydrogens in the half reaction. Charge is balanced by adding electrons to just one side. Solving full redox equations is done in the next lecture. And that completes the lecture. Where there is oxidation, there is reduction.